Hi, my name's Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this 21st of May 2023 to WindHexe Update 3, where we will be discussing a range of experiments done by various people and how that led to some thinking, clarification. And then after we've done that, we will do a little bit of paper review, but I will do that in a separate stream to keep these apart. So High Glass Chappie, D2105K, Artifact, John Weir, Terran Art, Ken Pratt, Louis Navarro, Gordon Doherty, Simeon Hein, sorry I get your name right this time, TP Sven, Space Case, and Rhett Oracle. It's great to have you here this Sunday evening in Europe and wherever in the day it is that you find yourself. And for those Antipodean people, welcome to tomorrow. So the image you're looking at on the screen here is another beautiful artifact that I took a picture of in the British Museum. And as I said before, I urge anyone that has an opportunity to go to London to go there. It is free. And this is an ancient artifact. Of course it would be. Hi Corky Goss. And what we have on it is this beautiful Vortex street in a closed loop, making the quadskelion that you find at the bottom of Tesla's Flower of Life flower pot. Very, very staged photo from his promotion of the weapon to end all wars that he was promoting. And so, yeah, it's like got this vortex street that goes round in a loop. And I see that as a torus, a fractal torus. And it has this, what some call a chrysanth flower, like a daisy in the middle. That is in the Akkadian and Sumerian kings. You'll find something very similar, and I'll talk about this another time, on the passport of the Japanese nation. You also see it in artwork representing power in many ancient cultures. What is it? I believe that that is the vector going down through that we call the Sothic triangle. A little bulb at the bottom is the destruction zone. So you need to imagine this in 3D. But I actually have, this is actually a 3D bowl here. So you can see here, it's a dome, and the vortexes are actually carved into the side curve of the dome. Yes, Neanderthal, that is the Anunnaki wristband one. Yes, the king that I've talked about in the past, the Sumerian kings, their stelae have many symbols of power, and this is one of them. Nothing on there is by pure decoration, in my view, points alone. Hi, Simon Claret. Simon Claret. Hi. Yes, Simon. I found out that he said that the chrysanthemum is the symbol of the Japanese royal family. I actually found that out when I was sitting down in Japan on my first evening in Hokkaido with Show's friend. It's a whole separate story, but it led to a sequence of really unbelievable, shocking events, which I'll package into a small story when I can get the media together and the time. So, how is everybody? It's been a little bit of a unpleasant week for those that didn't hear we have lost Dr. Takaaki Matsumoto. When I was doing the Ego Out presentation last week on the 14th, I had no idea that he had passed just 2 days prior. It's funny because before I wrote to him, ostensibly, to see how he was getting on, having had 2 weeks pass since he was ostensibly saying he was going to send me details of how he conducted his experiments. I also had sent, prior to that, and there was a kind of overlap with the reply emails, an email to Alexander Shishkin sending him some of the translated papers that I'd done of his work and his work with Kurols and Dubovik. And I said, look, I'd very much like to work with you, Kurols and Dubovik, to try and 3D visualize the understanding of the shell model of the atom and how that leads to the Usharenko effect, and also how that relates to some of the other stuff that we're doing, but also how it relates to the interplay in what he calls the atom battery. And that is that he is saying there is an interaction between what he calls background neutrinos, which are relic neutrinos, cold neutrinos, ultra low momentum neutrinos, but of the relic kind. He calls them background neutrinos, or they call them background neutrinos. And that there is to keep the atom stable, it withdraws energy from the quantum coherent condensate of this material. And if it's slightly depleted in the energy it needs, it captures that energy. If it's overexcited, it then sheds that energy into that condensate. And so I wanted to get better visuals on that. So I was asking if I could help him achieve that. He wrote back to me and he said, well, I'll see what I can do working with Kurols. But he said that Dubovik is extremely ill right now. I wrote to him again. I said, is he too ill to ask questions, answer questions? He said yes. I think we're going to lose Vladimir Dubovik quite soon. That is a real huge loss. I know at the beginning of 2018 he spoke about the death of Yuji Bajatov. And in that talk, he talked about hundreds, maybe thousands, I think definitely hundreds of papers that have not been published of his work. And given the quality of work that he has produced and the breadth of his work, oh my. That is some ego out. So anyway, I don't want to be too sad right now. It has been a difficult week. Taran, I don't think it's so much as coincidences. It may be this. Yes, you know what I'm talking about. But perhaps Dubovik's passing might encourage others who are sitting on a huge amount of potential ego out to really do all they can within their power to ensure that it sees a future, honestly. Anyway, just before I go on, I just wanted to say that I sat down here about to do my discussion tonight, and I had this on the top of my desk, and I actually read this. I got this for myself, Christmas 2019, and by Maury B. King, and I read it, the whole thing, sitting down in a Vietnamese garden in January 2020. And I had, previous to that, I'd just been to, I think it was December, the Global BAM conference that was held in Holland. And I met one, Dr. Michael Claridge here from the Sapphire Group. And I had his business card sat in here, along with some 10,000 dong in another place here. But I had it sat in here. And I thought I'd just open that before I started talking today. And I want to read you what was written by Maury B. King. I think it was in, when was it? Where are we? That's this version of it. 2018, this version, but it was originally done in 2001. And this is on page 101. And it says, the force-free vortex can taper like a tornado and concentrate an extreme energy density toward a point, making it a potentially good activator for zero-point energy coupling. I'll read that again. The force-free vortex can taper like a tornado and concentrate an extreme energy density toward a point, making it a potentially good activator for zero-point energy coupling. Such vortex filaments have been observed in plasmas, known as the filamentation instability. We'll talk about that in the second presentation this evening. And they tend to occur in counter-rotating pairs. Bostic also observed plasmoids to be formed in pairs with opposite helicity arising from plasma turbulence. Could such a model be archetypal and likewise represent vacuum polarization pair production from the turbulent virtual plasma of the quantum foam? Quantum foam conceptualized by John Archibald Wheeler in the 1950s, I believe, or certainly early. Then on page 103, another piece I highlighted back there in 2020, the analysis attempts to show that the poloidal rotation of the vortex ring could produce a large enough magnetic field to attract at the outer circulating electrons in a diachron slipping stream flow. The poloidal rotational velocity would have to be extraordinary, and the stabilizing ring would have to be an extremely thin filament to keep the poloidal electron velocities well below the speed of light. The calculated energy densities within the filament would be greater than a neutron star. So there's a lot of good stuff in here, okay? It's worth a read. But what I think I'm going to end on in this presentation is just that you kind of need to do what Tesla said, which is a snowball down a mountain. Or rather, what he witnessed. And that is to accrete without dissipation. And there's a couple of points in these early WindHexe tests that give a clue as to what I'm going to move forward with to try and explain what I believe needs to be done to do the more kind of magical things. Back to this drawing, or rather beautiful piece of ancient metalwork here. I kind of see this kind of structure as, you know, the Vortex street is at the top here, like in Henk's Vega sort of plasma based analog that he was working on, and that the flower and the central part of the flower is the notch out of the Sothic triangle. So it's about viewing points where you see these things. And of course, on the Tesla's flower pot, this was the foot stand, and then there were a cone, an inverted cone coming up with 4 points to hold around the center vortex line of the actual Vesica Pisces, which was cut, if you recall, at the point of up here, which I believe is the Holy Grail combined with the part of the Sothic triangle coming down. So there we go. Okay, so I'm going to go through the blog, and then I'm going to show you a new video by Tony Jabony. So we will pull up the blog first, and you can follow along because it's all been made public. Okay. So we've done a sound study. I need to work on the sound files. I got a little bit distracted with various things over the last week or so since going there, of course. But we have these wonderful high resolution sound files. Now, the interesting thing that actually Rob found was that in the patent drawings of the WindHexe, the insertion depth of the top tunable port, the outflow port, was the only thing that was at the golden ratio. And that was just, I think it's an interesting point to consider. So these videos I've all shared before, the can, the wood chips. Now, the steel can isn't expected to come apart anyway, but it's a good example in that particular test to show how it could loft something relatively heavy. And the wood chips, you know, if they were breaking up into smaller bits, you wouldn't know because there's so many of them. And we shared this video of the revision 2, which has there's several drawings here, and these are side channel blowers. Actually, this and the palette below, Tony got off GrabCAD, so this might not be the exact side channel blower that is used, but it is indicative. And so I did a video talking through that, but there's more sort of specific detail on here. You can see, and there's our cross section, and these are the deflector plates in here. Okay, and that's from above, and you can see the port here. So, hi Terran Art, hi Terran Earthling, hi Bringer of Change. Great to have you here. So, that's that, and this is actually from below, so you can see the deflector plate here, and the air would go in to those feeder channels, and here this is the slit. Okay. Now, Henk built a kind of like quick and dirty one to test flow. And it's interesting, his design's quite nice because he has this kind of, I think it's a paint can on the top here, plastic one, and inside he has another one of smaller diameter with slits cut in it. So he actually has a air distributor built in to this design. So he picked that up and built it in, and he ran some tests which we have shown, and we did a video about how it twisted up things in this sort of Gordian knot type thing here. And that as soon as I saw this, it reminded me, and this is one example, and I will give others, of the type of knotted structures that get formed in ultra if you do a short run, and this was in distilled water. And at the very least, it's aggregating impurities in there, but it is twisted into ribbons that are then twisted into this Gordian type knot thing. And I believe that it's the same kind of fractal vortex that's going on that's leading to this kind of thing. Okay. And there's some good points in here, and this will lead into what we're going to talk about here. He says the small pieces of carrot, and so he did some adjustment here in down here, and with the slits, and he ended up with the carrot being able to be lifted. It's relatively heavy for his airflow, and you can see it's a little bit dried. Well, there's air in there. It's not hot air, and it's not mashing it up into small particles, but it was certainly rounding it like you would imagine it would do in a ball mill. And again, you've got rounding going on with the aluminum, but the paper with the adjusted input ended up being a little bit more mashed up, as it were, as you can see here. Okay. And I have to say, this, as I'm looking at this here, it looks very much like another one of the things that was made in an ultra experiment, which I'll show another time, I guess. So it says here, the small pieces of carrot stay in the WindHexe analog better. They're still bouncing against the side of the cone. The air speeds are much too low to do some grinding when I see this happening. Much more pressure is not good for my plastic mini-hexe. It will blow up. I still think pressure is more important than flow. Okay. I kind of do agree with that, but I think it needs to be contained pressure. Like we are talking about here, you need to get it into a state where if you're adding more energy and you want to get that pressure, you want it to accumulate, but you want to accumulate in the torus such that it is not leaving. And he goes on to talk about something which I think is a good point. He says, the pressure energy builds the torus. Pressure creates the needed speed. With too much flow, with too little pressure, the air is blown out of the top and the bottom, which makes the torus unstable. I can see this happening with the toilet paper. Some is blown out of the top and from the bottom. This is what I think now the reason for the wide range where I see the pieces of carrot bouncing around. It feels like the air should stay inside the torus as long as possible to build energy in the torus and make the torus stable. But how to build the torus with air? I think I've kind of already shown you that, but it might not be obvious. And so I replied to not this, but something else. But anyway, I'll show you this. It feels like the air should stay inside the torus, but how to build the torus with air? I think I will try a different slit to reduce the flow. I cannot increase the pressure of my vacuum cleaner, but flow enough. So with reducing the port size, I might be able to improve it a little. I tried a different slit, tapered the port differently, maybe 2 times 15 millimeters. Different result again. Now the larger carrots pieces stay in. The whole hex is shaking with only a few carrot pieces in there. Holding the hex stable seems to make the content move faster. So, of course, if it's wobbling about, then you might get instability caused by, you know, the actual physical thing shifting and that moving onto the toroidal vortex that's in there. The paper gets smashed more. The aluminium gets grinded a bit. The blobs get smaller every time. The chimney does not make a clear difference yet. Need to do a few paper tests, toilet paper tests with different lengths of chimney. Okay, so he's talking about this port on the top here. Okay, so that is Henk's experiment there. Now, Cosmic Dave, thank you, Cosmic Dave, has done another one here, and it's an initial start of build. And actually, this is using, in my view, server cooling fans. I've actually got some in the other room. I meant to get them ready, and normally I have things by the side of me. Just bear with me. I'll go and get them. Okay, all right, forget that. it was attached to the Supernova, so I can't take that off. But basically, you can buy these kind of fans for computer server CPU cooling, and they're quite good because they run off 12 volts, but they're also very controllable, and they do have a high flow rate unidirectional sort of flow, okay, through this little port here. They're quite noisy actually, but anyway. And so his concept is to build one with a transparent top so he could look down into it and record what's going on. And he sent me this first initial kind of start of a build on 28th of April. And then today he sent me this with some notes. He says, today put an airtight acrylic lid on and ran 4 centrifugal fan motors. Note, a partial vacuum is formed below the base of the funnel, enough to draw up the aluminium foil balls. Next steps to plug in the various kilovolt supplies for added electrons and the ultrasonic pond mister maker and try different materials in funnel. Thank you very much, Terran Art, for the super chat. I have a 12 volt heater element. I may try putting in a fan intake. Lots of measurements to do, temp, airspeed and more. I also have a funnel with a low frequency loudspeaker for later experiments. We'll also add toroidal coils and various magnets. Lots to do. Construction notes. Airspeed of fans was measured at 12 meters per second each before lid and outlets added, and 7 meters per second at outlets with lid. Outlets are regular rectangle, simple slots. New cavitation outlets will be made and tested eventually. Okay, so I'm going to actually copy this and do it. I'll just watch on YouTube. Here we go. So I guess this is a piece of aluminium foil here, spinning around. He's looking through the top port there. And he goes down to an angle, get a different angle at it. Now on YouTube, actually, you can actually pause a video and step through it. If I pause this, you can actually step through one frame by using on your keyboard, it's either the full stop or the right, greater than symbol, the right arrow, but it's not an arrow, greater than symbol. So right, and then you can actually step back using the comma. Okay, I'm going to press play again. I'll zoom it on a bit. So we have a small, that's the Tony Jaboni's. So this is quite nice actually here. You can see the bouncing around going on in there. So it's really keeping that lofted up at the top there, isn't it? So remove my mugshot so you can see the full frame. Now what you can hear him doing is adjusting the speed right now. And he's brought the speed down, and you can literally see the aluminium ball moving down the cone. So really, it's quite flexible, having this nice control, being able to speed it up and slow it down. And the side channel blowers should be, better ones are able to control pressure and airflow as well. So these kind of things will be possible. He's blocking the port there. When you've got something desktop size, you can really play around with it. Okay, now you see it's down the bottom, and he's just turning the speed up, and now it's whipped up to the top. So he turned the speed down, it went all the way down to the bottom, and he turned up the speed, and it went all the way up to the top. Yeah, we'll talk about Polestar in a little while, Rhiannotle. And we'll also talk about the Cavi-jet nozzles. Now, ideally, you kind of want to set this up so it stays at the top, maybe, but it's actually not really interacting with the walls of the chamber. You want it kind of to be just in the vortex. Okay, so I think he turns down the power here or something. You can see there's some fragments of aluminium here or something, and he turns down the power and they drop out. 3 little aluminium balls there. Okay, all right. So I did this presentation. I don't know if you've managed to see it, but it was on a thing called the Cavi-jet. And this was actually developed and it was first announced, but it was patented and it was used for mining in the oil industry. I think it still is probably. And this paper is from 1984. And it's about creating solitons in a water jet by creating a self-resonant structure like an organ pipe, but with a particular contour that leads to the self-resonant phenomena that leads to these solitons, these vortex solitons coming down. And I believe that this will be possible to apply this to HHO, and I'm had a little conversation with Slobodan Stankovic, and I believe that he is going to explore this, and if it is able to increase the cutting speed of HHO, that will be very impressive. Now, I included this image here on the front cover, which is covered up by the YouTube logo. But this is a velocity and pressure distribution of an inline Rankine vortex. And what is that, a Rankine vortex? That is actually a slot type of vortex. And so that is the type that we have currently in the WindHexe devices that we are looking at. And the papers that you need to look at here, cavitating and structured jets for mechanical bits, increased drilling rate, part 1, theory and concepts. And this is the application experimental results. I think they found 4.3 times the depth of cutting with the same input power. And so what I'm saying is that when you are injecting a continuous flow, it's kind of like it can't do much damage because you're only getting the power of that continuous flow, which is not a peak, and there is no separation between the intensity. It's kind of almost like a steady state. Inserting these vortexes, it's able to compress the power into pulses, and it's like a hammer drill. And so they found it a lot more efficient for mining. And the example they gave was calcium carbonate. And of course, if you've got water and it's going past a metal is hydrophilic, water against metal will produce easy water to a degree. So these will be effectively, with the polar molecule and the easy water, these will actually be subtle fractal toroidal structures, but mostly they will be a charge going around this way, and then you've got the current. It's basically a single toroidal moment, but it's kind of self-supporting itself. It holds itself together, and so it packs a bigger punch. So rather than it's kind of like, you know, an endurance runner can run for an extremely long time, but if you ask an endurance runner to sprint, you know, and then run slowly and sprint and run slowly, you might find that it completely breaks their ability to do the distance in the time they ordinarily do, because they break their body's ability to cope with a certain amount of, you know, stress. And it's like a hammer drill. If you're ever using a drill and you're trying to drill into a wall, and you're just using it on the normal drill mode for like drilling into wood, for instance, or drilling into steel or whatever, then, you know, you try and do that in a wall and it kind of doesn't really do anything. You kind of need the hammer drill, and it to a degree it's pulling the material out, but it's punching it as well as applying the rotational force, and it's the punch that kind of helps you get through the wall. So it's kind of that kind of thinking. Now, after I posted this, Tony Jabony, and I would have liked to have done this sooner, but this was 18th of May, and we're only on the 21st of May, but I think within one day, Tony Jabony came back with a design that learnt from this, which we're going to go and have a look at now. And here it is, or it will be when I show you. Okay. So it's a rather lovely thing. And this is intended to be a kind of very, very small device. And the main part of it would all be 3D printed in metal. And you would put the shop compressors on here. So the side channel blowers are going to enable 10 times the amount of airflow compared to the volume of the current large WindHexe. When I say large, it's obviously small compared to Frank Polivka's. However, this, by making this smaller, this will have the kind of volume to flow rate ratio, or, you know, that will be much higher than the current version that we have been testing. And so it'll also have the pressure behind it. So if we actually look at this, it's rather nice what he's done here. Looking through the top port, and here we are with the cross section there, and he looks at it with the sectioning. And if you go in here, this is the Cavi-jet here. Now, I don't know if he specifically calculated the resonance structure here based on the formulas that are presented in the various papers, but if he did, that's great. If he didn't, then that needs to be done. And here we go. That's the Cavi-jet. So essentially, you've got the pressure coming in here, but it's doing a pulse in the soliton. Now, the soliton going in would have a it's basically condensing the energy from a certain amount of input into a self-organized structure that has this extra punch. But it's also it's already stable. So what you're doing is you're feeding a stable structure in here, and then you're feeding it in here, you're feeding it in here. So there's going to be a whole train of stable structures, and they have a flow rate going through the center, but they also have this pull behind that I've talked about so many times. Okay? And when I looked at this design, I thought possibly there may be a challenge with it. Now, this might work. It might work. But intuitively for me, if you are putting a toroidal soliton in here, and it comes in here, and you know it's going to be not that big, but it comes into here, it's going to target this area here. And these solitons like to travel a distance in ignoring the air flow around them. But when it hits this side wall here, one side of the soliton is going to experience shear forces, and it's going to destabilize it. So I immediately came back and said to Tony, look, I think this is great. It might be the way it will work, but I suspect that what you will need to do is to fire these into the center of the channel, okay? Rather than directly into this wall over here. Yeah? So if you go to the start here, you're really, at the moment it's targeting the wall, but you want to kind of target the center of this channel here. Yeah? So maybe we can look at it from a different angle here. Yeah, okay. So, yeah, it's coming in here. It's going to hit here. Coming in here, going to hit here. And I believe that you'll go to all the effort of making these self-resonant structures, and it'll be pulsing in here, but it'll be breaking up on this wall before it can join its friend over here. So this should really come in at a slightly different angle. It's going up. I think the kind of incline here is correct. It's correct. He's firing that into the kind of center area up here, but he's not firing it into the center of where you want the core of the overall vortex to go. Yep. Okay. So with that in mind, there's some schematics here, which is rather nice. So thank you, Tony, again for your hard work to put this concept out. Now I'm going to go and get a couple of comments that I made and the justifications I made for what I've just said there, which I wrote in a reply to him. So give me a second, I will find that. Right. Give me a second. Okay, it's not this one. Okay. So I said to Tony Jabony AKA Robb when he sent it through, I said, ooh, I like this. Perhaps the gas injection should be more into the center of the channel than the side. I don't think you want the shear on one side of the injected resonant solitons. It might disrupt them. I think you want them to chase each other and pull each other into them, like we see in Suhas Ralkar's ultrasonic fluid tank in 2017 in Mumbai. That way, they accrete strength rather than disrupt themselves and potentially each other. So, what am I saying there? Let me show you this video that I hope will make part of the point that I need to make here. I'm going to kill the audio. Okay, all right. So this is sprites from 2017. And let's go through this. What happens here, and this is one of these examples where I'm talking about the fact that the particles around here drift around like they don't care what the solitons are doing as they're going through. Here's a soliton. And what you can see is, for instance, there's this one here, and it pulls this one in from behind. Pulls it in. They seek each other out, but they seek each other from behind. So I don't know if you just saw that one. Here, I'm going to step through this. So, right, there's another one. There's a couple that merged up here. And then they move down, and is it not going to do it? So two are merging over here. Oh, well, what have I done there? I don't know what I've done there. What happened there? Oh, dear. Okay. No idea what happened there. Give me a sec. Okay, all right, fine. Okay, you'll see these. You can go and have a look at this yourself. But essentially, they like to chase each other. There's two of them that joined up together. And they form one. They aggregate. Yeah, two joined themselves there. A whole bunch of them joined up together. They will do if you're looking at them. See, two joined themselves over there. Joined with each other. Whole bunch of them joined together. Doing. Okay, I think you get the idea. They like to chase each other and then join up into one unit. And it's always the one in front pulling in the one from behind. And this is what I'm saying. It's like they want to move forward, but there is a depressurization zone behind. And this is, it would appear, being verified by our experiments and by those of Polivka and by the experiment of Cosmic Dave in the UK. So from behind, there's this depressurization zone, and that encourages the ones that are slightly from behind to go and leap and jump and merge into the one that's in front. So they kind of like help each other accelerate into each other. Right. Now, of course, these are going in every kind of direction. That's not really ideal. But if we go back to Tony's video, if I've still got it up. Let's see if I've got it up. So, if we go back here, and if you can imagine, rather than pointing to this wall, it was pointing to the center of the channel. That when this one shot one in, if there was one already coming around here, it would want to join into that one. And then if this came around here, this one, if there was one already here come from this one, it would join into that one. And after a while, they would, you know, because of the phase relationship, you might find that they're always trying to chase the one in front, and they're chasing the one in front, and everyone that comes in is wanting to chase the one in front, and it's building strength, and it's building strength, and it's building strength, and it's building strength. And so, rather than the problem that was identified by Henk, that it seems that if you put too much airflow in, it comes out at the top and the bottom, and you need the pressure. I actually would say you actually need the self-organized air. So you can add air at a potentially a lower pressure, but it accretes that strength like Tesla saw in a snowball going down a mountain. The solitons are able to accrete. Now, we don't have this luxury in the ultrasonic tank in 2017 of Suhas Ralkar, because they're kind of coming out, okay? So it's only when there's one kind of semi in the right line to get into the Sothic triangle and be pulled in and merge with the one in front. But here, when you have the quad scallion going on, you can be adding energy in. Okay, so I continued with my argument. I said, this is how they inject plasma into a tokamak. They do it with what's called spheromax, a plasma torus. Okay? And then I give a link to spheromax, and this is what I'm going to talk about in the second part of the presentation. And then I say, to further illustrate my point, I've got a couple of other examples here, and I will get those up. Give me a second. So the first one is my title slide for the Seek and Share presentation in Sochi, where I gave the first third of O-Day slides. And you can see over here on the right, the so-called how the sun works. This is a cult, apparently, that believed that this symbol represented how the sun worked. And this was prior to the birth of Christ. And this, I think, is 400 Anno Domini in northern England in Ilkley Moor, the same symbol. But there's many of these carved into the rock. Now, this is a torus, okay, going this way. It's a yin-yang, and it produces a torus that goes this way that has the vector down. This is our WindHexe structure going on. And we want to kind of inject the torus to join the big torus to become the very, very intense vortex going around this way. Okay, so that's one example. And then I have this next example here. Oh, no, that isn't kind of it. So it's just, I don't know if you can see it, but it's the 4-point up on here and how it pulls it in. Okay, now I've got something in my head a few moments ago, and I don't want to lose it, and I might have lost it. What am I saying now? Right. Yes, so it's in the same Seek and Share presentation, and I don't want to lose what I've got in my head. Let me put that down. Okay. Okay. So this is again in the Seek and Share presentation. So here, this is in Lafferty vacuum arc discharges. This was the main, or one of the main references, or I think the main reference of Ken Shoulders when he started to investigate what John Hutchison had done. And you can see here they are adding in, this is a single sort of torus structure, and then this is a fractal torus structure, and this is with 3 points and 4 points, and it's got an equation here. And why I think this is important is because depending on the number of inputs you have, there will be potentially a resonant structure. So it's not just that we want to input these things in such a way that the energy is not lost and dissipated by shear forces colliding with the sidewalls or impacting each other and destabilizing them. You want them the phase relationship of them coming in such that the one in front can pull the one in from behind and accrete and accumulate the energy and the compression and the fractal vortex going on. And I believe to do that, there will also need to be a resonant size that we need to produce. So this is where it might start to get a little bit complicated. This is where we're getting into the weeds. And I don't like to show equations, but this shows in terms of cathode spots that the more spots you have, the more they organize. Okay? Now, the key point here is they are equidistant. So that's one thing. So if we've already got them equidistant on our structure here. These are equidistant. So that part is correct. And we might be able to compensate for the size by changing the phase relationship that these come in. And that might just be changing the pressure that comes in on here for the rate at which these things are injected. Okay? And that might just be all you need. And it might be that the sweet spot is that which allows the injection of a soliton of air such that it doesn't disrupt the formed structure. Okay? So I think the key part is you have them equidistant, and then the tuning part, other than the tuning so that your Cavi-jet here is resonant to be able to produce the toroidal solitons of input air, the resonance will be when the pressure is or the flow rate is such that the solitons of air come in so that they can accrete rather than disrupt the soliton that forms in there. And then we will not get this problem that has been identified by Henk, that if you increase the flow rate, sooner or later it's not keeping itself in the torus, it's just blowing out of the top and the bottom. It's not being added to it. Okay, so we need to structure the air so that it can self-organize. Okay, the toroidal Cavi-jet injection will produce air that does what we saw on that video here, not this one, this one here, where it accretes. Now, this is obviously in water, which is a fluid, and so is air. So it's quite similar. But I actually want to refer you to a different example by one Paul Collock, which brings us to SWIFTBIC, which I will talk about in a separate stream that I will launch after this. And things will get very, very interesting indeed, I believe. So let me just pull up this one by Paul Collock. I need another window here. No, I'll do it in here. It's fine. No, I'll put a new window here. No, I'll do it down here. So the idea is to build that snowball going down a mountain. It's not losing its ability to destroy. It's accreting force that it can apply and do work with. It's like the Tacoma Narrows Bridge. It's a little bit of wind and it just is not losing it. There's no damping going on. So it just accretes and accretes until it smashes things up. Hi Polygon. Hi Bernie. Hi Ken Pratt. Hi Daniel Foster. Great to have you here. Hi Glitched as well. Great to have you here. Okay. Right, so I want the paper, the presentation by Paul Collock. Let me have a look here. Give me a second. So, hopefully this will do it. Let's see. Probably have some annoying advert at the beginning. So this is a patent from 1973. I've discussed this before. It's this presentation. Now it's a patent-free way of make and control large-scale EVOs here. And if I can go through, there is a description. Here's the toroidal and the poloidal gubbins going on. And here's the overall, what is called in, and we'll see this maybe in the second presentation tonight, you'll see what's called the separatrix which is this boundary layer, the separatrix, okay? And this is my point here, is the way they describe this, and this is how it's thought about in modern physics, is, and this is what I was talking about here in this, where it says, such vortex filaments have been observed in plasmas known as filamentation instability. Okay, so what you have here is you have a discharge between a cathode and an anode in pre-ionized gas, if you could see it. Cathode and an anode, or vice versa, in pre-ionized gas, source of ionizing energy. This can be electrical discharge, this can be radio frequency, it can be, as it was in the PAP engine, it can be a radioactive isotope. So that causes pre-clusters in the air, like you get in a lightning storm caused by charge in the air. And then you discharge through that charge, so you've already got charge clusters in there, but that's not discussed. They just discuss about the discharge between the cathode and the anode. And what happens is you get what's called kink instabilities. And so that is one of the types of filamentation instability. Okay, so there's a filament of plasma that goes between the cathode and the anode. This forms a filament instability, and there are multiple of them here. And the way this is thought to work is that one instability forms and another one forms, and they align themselves because of their magnetic and electrical moments. And then what happens is you get reconnection at this point and in this point and in this point and this point. And then just as happens in the fluid dynamic system that I was just referring to by Suhas Ralkar of that video I took in 2017, these merge, and the current that you get in the center of this, is added together. It's accreted. The power and strength is accreted, and that is how you form a plasma. In fact, I've actually got the quest for 0 point energy here, okay, in this video. So okay, so that's basically the point, is the kink instability and then merging. Right. Now, this then led to a discussion where Henk said, you know, it might be easier to use a generator because of the power and stuff. And I said, well, yeah, so you can get, like, for a fairly reasonable amount of money, like €1,000, you can get like I think it's like a 6.5 kilowatt diesel generator, 3-phase, 400 volts. Or you can get like I think for €2,000, you can get like a 10,000 watt, a 10 kilowatt, or it might even be more. I think even like 15 kilowatt at 400 volts, 3-phase. And this could run the side channel blowers. But as I think someone said the other day, they were considering combining some ideas. It would also, if we are to believe Malcolm Bendel and Paul about the GEAT, Paul Pantone, the fuel is only getting the work you get out of your, let's say, your diesel is, let's say, 30% of the energy that could be yielded from that burning process. And what the GEAT is often doing is recovering some of that thermal energy to excite the material going in and so on. So think about this. If we combine some concepts that are in the GEAT with what's going on in the WindHexe, and this may actually be exactly why Frank Polivka used a diesel generator, because you can hear it going on in the background. If you take the exhaust heat from your generator and you counterflow that with the air that's coming out of the side channel blower, you are going to heat the air using the exhaust from the generator. Plus, the air is from the air, so it will have water in it, it will have some moisture, and you will have moisture, obviously, coming out of the burning of the hydrocarbons, and so you will have moist air with metal involved, which means, and if you've got counter-rotating vortices, you will charge the air that you are putting in. So, with just using a diesel generator, you solve your necessity to have a connection to a very high power 3-phase power supply. You solve potentially your need for a heat source for your heat exchanger, and potentially you solve your need for a way of charging the air that's going in there. 3 aspects in one. And this could enable potentially a WindHexe on the back of a truck. A WindHexe on the back of a truck. Okay? Now, if you have charged solitons here, okay, going into your WindHexe, okay, with your Cavi-jet, yeah, they are coming in and you have the right pressure and phase relationship such that they do what we saw in the cavitation system of Suhas Ralkar, or in the patent, which is now patent-free, of Paul Collock from 1973. Imagine, rather than our kink instability rings here, with their charge running through the center, these are in fact our Cavi-jet injected charged air pulses at a higher temperature coming in. They would do exactly the same thing. They would join together, and the more you put in, the more they would accrete, up to a limit of which, you know, the system can handle. And then you don't have this air leaving, it's wanting to stay organized. And so that is my proposal. 1, we inject these at an angle in. 2, you are using a system that blows the air in, but also the power that's used to generate that is, I mean, if you use electricity to compress air, the electricity you get from the mains, you've already lost 50% of the power that generated that if it comes from a higher hydrocarbon, right? So, if you can burn diesel directly in your generator and you are recovering a good proportion of that heat, then you are way more efficient than the compressed air that you would get by using mains compressed air. But the bonus is you can have moist air going in to the side channel blower, and it's definitely moist air coming out of the internal combustion engine. Counterflow these things, and it will need to be counterflow. Why? Because just like in a condensing boiler, you want the hot exhaust going in at the hottest end of the gas, and it goes down to the coolest bit where you've got the coolest gas coming that way. So the counterflow, and that maximizes your heat transfer between the two. And if you've got a vortex going one way, a vortex going the other way, you're going to have your charged air coming in, and they will accrete. I have no reason at all to expect that it wouldn't do the same thing as Paul Collock observed, and is the basis for spherical fusion reactors, as you will see in the second part of my presentation tonight. And it will do the same thing as is observed in this fluid dynamic system. And given the fact that if we can get we've already got the equal spacing between our input ports, all we need to do is to get the pressure relationship correct between these as they're coming in. And I think it will just accrete, and it will accrete, and it'll accrete. And I think that will get us very close to what we are wanting to do. So that's what I wanted to do with this presentation, the first of the 2 presentations today. And I will launch a new stream in about 19 minutes. So look out for that. I might not trailer it on remote view. I might just launch the stream, so it will be on YouTube. So look at it. You look at it for it on YouTube. Any questions at this stage? I'll give 4 minutes for questions. So Gordon Doherty, I don't think this is GeekHex. I actually think Frank Polifka's system did this. Yeah, the space case, the Cavi-jet creates a pulse jet anyway, so it's already built in. Well, Gordon, you've had the nice part of the presentation. That, well, actually, no, there's some awesome things in the next presentation, but they need to be separate. Okay. Polifka, I think, it sounds like a Polish name, but he grew up in Kansas. WindHexe is German for wind witch, basically. WindHexe. WP for Truth is doing a full-on mashup. You should do an album. Hi, Watkins Incorporated. Hi, Alex Del Castillo. I'm quite excited about the fact that we might be able to make this a mobile unit, which means that when you're doing recycling or you're generating soil for people, or you're doing, let's say, on-site concrete reuse, I think that's quite exciting. You know, don't move the mountain to Mohammed, move Mohammed to the mountain in this case. So more efficient. Yes, John Weir. Tesla's fabled earthquake machine. This is exactly the point. If you can build the strength of the system, it will vanquish anything if you don't have losses in the interim period of time. And material is able to withstand so much, and it can, like, you know, you can have a bridge and it can support its rated load for 100 years, 200 years. But if you just go once, for instance, or a couple of times over its rated load significantly, you end up causing the bridge to fall apart. And so that's it. You're finding a way with less power to get to a point at which you reach a critical threshold in whatever it is you're trying to manipulate. To be fair, I'm not saying that Frank Polifka had a Cavi-jet in his system. It might have not been necessary for him. You just need a big airflow and the charged air and the hot air. And that, it would seem that we're already in some early prototypes able to at least break up tissue paper. So it's kind of like the principle's there. You just need to take it up to the max. But what the Cavi-jet showed in 1984 is that it can dig a hole in limestone 4.5 times or 4.3 times deeper for the same input power and same parameters of the water pressure. Okay, so if you can do things, you can achieve the same effect using 1/4, let's say, of the, or do four times the amount of work that you are desiring to do with the same input power, or do it 4 times quicker, let's say, then who wouldn't want that? If you're already talking about removing the water from the say the vegetables that you're trying to produce a powder from, and grinding them for just the power that it would take to normally dehydrate that vegetable, if you can do that for 1/4 of that, I mean, you're talking about super efficiency. Thanks, Terran Earthling. There are cyclone pipes which have just one input, but they are not this structure. So they're basically just one input over here. So they won't be able to. The cyclone pipe, the air comes in and it goes into a cyclone, right? It goes into a vortex. There isn't the ability to build the strength of a toroidal vortex or a fractal structure with that. Yeah, 4 pressure. Well, I mean, 3 would be okay, I guess, but 4 pressure washers maybe. But I think that's what they use. The Cavi-jets that they're using in those tools for drilling oil wells and stuff, they're not just one Cavi-jet nozzle. There's multiple ones of them, right? So it's basically what you're saying, I think. Okay, so what I'm going to do is I'm going to pause now, and I will launch a new stream in a little while. So look out for it. So thank you very much again for the super chat, Terran Art. That really helps. And thanks again for your time today, this evening. This was WindHexe Update 3. And this beautiful bowl here is, I believe, giving us a clue. This quadskelion, this vortex street in a loop. And you build and build and build the strength until you get this moment that does the work. Same thing at Tesla's foot of his flower pot that is based on the sacred geometry. So thank you very much for your time, and I will see you in the video in 10 minutes.